The topic is scaling of MOS circuits. There are three models for scaling, that is constant electric field model, constant voltage model, and combined voltage and dimension scaling model. It is a combination of about two models. So there are two scaling factors in order to scale the MOS circuits. First one is alpha and another one is beta. Scaling factor alpha beta is used for scaling supply voltage VDD and gate oxide thickness, and whereas alpha is used for scaling all the linear dimensions. Whereas in constant field model, beta is equal to alpha, and in constant voltage model, beta is equal to 1. So, what is the use of these scaling factors? These scaling factors help us to improve the uh, figures of merit of the transistor. These are six are the figures of merit of a transistor. So, the figures of merit are minimum feature size, number of gates on one chip, power dissipation, maximum operational frequency, die size, production cost. These are the six figures of merit in order to scale the CMOS circuits. Next one is scaling models and scaling factors. We can here you can see the NMOS transistor where the length, thickness, and width of the metal layer, that is polysilicon layer, are scaled by alpha as they are the linear dimensions. As I told that the thickness of the oxide is scaled by beta as shown here. Like this, the linear dimensions are scaled by alpha and the thickness of the oxide are scaled by beta, and as well as the supply voltage is also scaled by beta. So now we have to derive the scaling factors for each and every parameter of the transistor. So the first parameter is gate area. Gate area is represented by AG. AG is the product of length into width. So the length is scaled by alpha and width is scaled by alpha. That is equal to 1 by alpha into 1 by alpha. That is 1 by alpha square as written here. The next parameter is gate capacitance per unit area. That gate capacitance is given by C naught equal to epsilon oxide by D. D is nothing but thickness of the oxide. As thickness of the oxide is scaled by beta, we write it is scaled by beta. As it is in the denominator, we write 1 by 1 by beta, that is equal to beta. Therefore, gate capacitance per unit area is scaled by beta. The next parameter is gate capacitance, where here the length and width are considered. In the gate capacitance per unit area, the length and width are equal to 1. So the gate capacitance is given by Cg, that is equal to C naught into length into width. Cg is scaled by, so the C naught already we have seen that it is scaled by beta, and length and width are scaled by 1 by alpha into 1 by alpha. So totally the gate capacitance is scaled by beta into 1 by alpha into 1 by alpha, that is equal to beta by alpha square. The next parameter is parasitic capacitance, is represented by Cx. It is proportional to Ax by D. Ax is nothing but the area. D is the distance. So the area is length into width. So both are scaled by alpha. So it is given by 1 by alpha into 1 by alpha, 1 by alpha square. Whereas the thickness is scaled by alpha. So as it is in the denominator, so it is 1 by 1 by alpha. Alpha and alpha get cancelled. So it is equal to 1 by alpha. So the parasitic capacitance is scaled by 1 by alpha as shown here. The next one is the carrier density in channel. It is represented by Q on. Q on is a product of capacitance per unit area, gate capacitance, and into VGS. VGS is nothing but an voltage. Where we saw that voltage is scaled by beta. So it is scaled by 1 by beta, whereas VGS is scaled by 1 by beta, and C naught is scaled by beta. So beta and 1 by beta gets cancelled. Therefore, the carrier density Q on is scaled by 1. Okay. The next one is channel resistance. The same way, the channel resistance formula should be written according to the parameters and of the channel resistance. We scale the channel resistance. Even the channel resistance is scaled by 1. These are the parameters which are going to be scaled. So go through these all parameters, and then uh, these are all the parameters, and then at last combine voltage and dimension and constant electric field and constant voltage field. We have to derive the parameters. We have to derive all the parameters, that is scaling factors. For the supply voltage, it is 1 by beta. So in the constant electric field, beta is equal to alpha. So beta is replaced by alpha. So in the constant electric field, the scaling factor becomes 1 by alpha. In the constant voltage, the beta is equal to 1. Therefore, if you substitute in this 1 by beta, so 1 by 1, it is equal to 1. In the constant voltage, the scaling factor is 1 for supply voltage. In the same way, all the other scaling factors are replaced with the respective conditions. We get the expected scaling factors in the constant electric and constant voltage field. So in this way, all the scaling factors of every parameter of the transistors are scaled. So I'll attach this PDF in the description link. You can go through it. So this is about scaling of CMOS circuits. Thank you. Like, share and subscribe to my channel to get more videos on digital VLSI design. Thank you.